Briefly introduce it. Okay, so thank you everyone for joining this seminar. So let me introduce today's speaker, Dr. Erbo Jampisov from OIST here. He is currently a postdoc in my unit. He got his PhD in 2022 from University of Tokyo. Today, he's going to talk about a joint work with me on Liouville type theorems for fully nonlinear PDEs. So Erbo, please.
Thank you for the kind introduction. First of all, thank you for Professor Tran to give me a chance to talk here. And also thank you all the participants for coming to this talk. Okay, so today I would like to talk about Liouville type theorems for fully nonlinear elliptic and parabolic equations with boundary degeneracy. And today's research is joint work with Professor Chen Liu from OIST. Okay. So in this talk, we consider the following fully nonlinear elliptic equations. Later, I also explain some results about parabolic case. But first, let us consider the following elliptic equations. Here, the equation is the unknown function u plus f of x and the gradient of u and the Hessian of u is equal to 0 in omega. And here, this omega is possibly unbounded domain of the usual Euclidean space. And the dimension is always greater than or equal to 1. And the function u is from omega to r. And in this talk, we always assume this f satisfies that f of x and 0, 0 is always 0. So by this condition, we can see this equation always has the trivial solution. I mean, if we put u is equal to 0, then the identical 0, it's a solution of this equation. And I want to remark here that we do not assume the boundary condition. And so actually, this is the important feature of this talk. We don't assume the boundary condition, but instead, we assume some degeneracy of this operator f at the boundary. And actually, this degeneracy generates some boundary condition. I mean, Drucker boundary condition. So today, my aim of this talk is to under suitable assumptions on F. We will show that the trivial solution is actually the only bounded viscosity solution of this equation P. Yeah. So later I will give some examples of the equations. So, but here we just consider this form. So first, there's a known results by Biagin Punzo in 2023, and they consider the following equation, the singlet coefficient equation. So the equation is the q of x times u minus Laplacian of u and the inner product with bx and gradient of u is equal to 0 in omega. And they assume the boundedness of the domain and the coefficients of q and the coefficient Q is a continuous function defined on omega, and B is a vector valued C1 function. And they assume that if this coefficient Q blows up at the boundary at the rate of the quadratic rate, then here, so dx is, we often use this function dx, and this is the distance function from x, and x is in omega, and to the boundary. So if the coefficient q blows up at the boundary at this rate, and also we assume some condition on the coefficients of first order, then the solution, the identical zero function, is the only bounded classical solution. So actually, we were motivated by this result and started to study some generalization of this results to viscosity solution. And yeah. So in our equation, so we want to generalize these results to more general equations. We assume some conditions on operator F. So the first one is the continuity of F. So the operator F is always continuous in omega and R times Rn times Sn. And here the Sn is the n times n symmetric matrix, the set of symmetric matrices. Since we want to deal with viscosity solution, this is a natural condition. And the second one is also a natural. So we assume some ellipticity condition on F. I mean, for any x in omega, and also p in Rn, and also for any symmetric matrix x and y satisfying this inequality, but always f of xp capital X is less than or equal to f of xp capital Y. So if we consider Laplacian, then this means so the sign should be minus for Laplacian. And the third one is the most important condition in this talk. So here we assume the degeneracy of the operator on the boundary. And this is for any modulus of continuity omega. F satisfies this convergence. So I mean, the absolute value of F, if you take supremum over X, but this X is actually near the boundary. So later this delta tends to 0. So X is near the boundary, and the first order term satisfies this inequality, omega of delta over delta. And also the condition on Hessian satisfies omega delta over delta squared. So okay, later I will explain these conditions, but roughly this means the coefficients of the equation and the coefficients of the first order term tends to 0 at the rate of first order. And for the second order term, the coefficients tends to 0 at the quadratic rate. And the last one is the existence of zero solution. I mean, it's like f of x 0, 0 is 0. But if you consider only bounded domain, this condition, in this first condition, we only need this equality. But since we deal with also unbounded domain, we need additional, stronger assumption here. So this is if p and capital X tends to 0, and the supremum over the domain, the absolute value of f tends to 0. Right. So basically, we assume these 4 conditions, and we want to show some Liouville type results under these conditions. So here I have several remarks. So first one is as I said, by the first condition, the trivial solution is a solution to P always, because even in this condition, F should satisfy this condition. So this means 0 is always the solution of the equation P. And also, I want to check here the connection with the previous results. So the equation by Piaget and Puzo. So this equation, if we divide this equation by q of x, and we write this like this kind of form, then this 1 over qx goes to 0 at the boundary, right? So actually, we can check that this equation q, if we write down in our way, it's like this: f of x p capital X is minus 1 over qx and trace of capital X, and minus 1 over qx and px times p. And in this case, our third condition, f3, corresponds to this convergence. I mean, since we take a supremum, this term is like omega delta over delta square. We just write delta as a distance function. And then the third condition corresponds this convergence. And but if we assume the assumption 1, so this is the assumption on qx and also p of x, and then the third condition is satisfied. So actually, our condition covers the previous results. Okay. So let me explain our theorem, main results. So for the equation P, so the equation P is this one. So let omega in Rn be domain of C1 class, and assume that the 4 assumption on the operator F hold. And if U in continuous over omega is bounded, viscosity solution to P. And also we assume this solution can be continuously extended to boundary omega. Then 0, U should be identically 0 in omega. So this is our first result. And okay, and actually in our paper we have another form of main theorem, and yeah, if you call it theorem 2, then in that theorem we don't assume this continuity after the boundary, but to prove that we need actually another assumption on F, but it's very complicated. So in today's talk, I skip that assumption on F, but actually we can tap this assumption in the second theorem. And in most examples, we can show that this additional assumption holds. So let us briefly recall that the definition of a viscosity solution. So I think many of you knows very well, but yeah. So we call that U. Here we assume just continuous function. But U in C omega is a viscosity subsolution of the equation P, if and only for any x0 in omega, and whenever there exists this function, C2, this function such that this U minus phi attains a local maximum at this point x0. U of x0 plus this, if we put the gradient of this phi into the equation, then the left-hand side is always negative. And the continuous function is called a viscosity solution of equation P if this function is both a viscosity subsolution and also a viscosity supersolution. Right. And for this main theorem, we have several remarks. So first, the boundedness assumption of solutions is necessary because if we consider a very simple example, it is obvious. So if we assume the domain is unbounded, so for example, so I forget to mention that. So we in this form we write down the second derivative of Hessian of U, but we also admit that the equation is first order. Yeah. So first order equation is also included in our results actually, and so if we consider the first order equation, very simple first order equation, like this. So U plus the distance function D times the absolute value of U prime is equal to 0, and one dimension case. And then yeah, U of x equal to minus x is always a solution to this equation. And actually this equation satisfies our 4 assumptions on the operator. It then degenerates at the boundary on the first order, at the rate of first order. So we need the assumption, the boundedness assumption of the solutions always. And like I said before, yeah, this is about another theorem of ours. So assume in addition that omega is bounded and also C2. And if we assume another some assumption on F, then actually we can prove that this equation, the solution of the equations are uniformly continuous. So if the function is uniformly continuous, then of course it can be extended to the boundary continuously. So we can use our theorem 1, right? So I mean, if we assume another condition on F, then we can show that our assertion of theorem 1 holds under just continuous function in omega, not up to the boundary. We just need the continuity inside the domain. Okay, and the third one is the key observation of our proof, for our proof. So yeah, if U is a solution satisfying not zero at the boundary, in some point at the boundary, then you cannot be extended to C2 function around x0. Actually, this is obvious if we consider some examples. So if you consider this kind of equation, if U is a C2 function at the boundary, I mean, if x0, here, if U is a C2 function, then the Laplacian of U at the boundary is bounded. So if x goes to the boundary, then of course this term goes to 0. So we can have the U is equal to 0 at this point, right? So if we consider the C2 omega bar, then our result is very obvious, actually. So we can say that if there exists a solution to our problem, the gradient of U and also the second Hessian of U must blow up at the boundary. Yeah. So we can check this also for our equation. So 0 is equal to, so this term is always 0. If you take the limit, so x is inside the domain omega, and if you take the limit to the boundary x, the boundary point x0, then actually by the boundedness of first order and second order of the solution, and also our assumption, degeneracy assumption of f3, actually this term goes to 0. So this is equal to ux0, but we assume that ux0 is not 0, and this is a contradiction. So first order, I mean gradient of U and Hessian of U, I must blow up at the boundary. So let me explain some examples. So actually our result cover several examples, and I will explain here 4 or 5 examples. And so first one is first order Hamilton-Jacobi equations. So, and also we admit that the power type nonlinear here, and assume that m is greater than 1, and u is just continuous function in omega. And this u is a bounded viscosity solution of Hamilton-Jacobi equation. And if you check the third condition on operator F, then the coefficients has to tend to 0 faster than this first order term. So we need the assumption mu is greater than or equal to m. So if we assume this, then actually this equation satisfies all the assumptions on F, and also the assumption I didn't explain the fifth assumption on F. So we just assume that u is continuous, not at the boundary. Then 0 is the only solution to this equation. And also we can check that our condition is optimal. I mean, if this condition does not hold. So this condition comes from third assumption on F. And if mu is less than m, and if we consider just one dimension case, then actually we can solve this equation in classical sense. So we can write down the explicit formula for the equation. So actually, if we consider first order, no, I'm sorry, not first order, one dimension case, then this function is actually the solution of this equation. So, and also this is bounded, and actually this is classical solution. And the second example is the Laplace type equation, but of course the coefficients must tend to 0 at the boundary. So if we assume u, a continuous function u, is a bounded viscosity solution of this Schrödinger type equation, I mean u minus dx part mu, Laplacian of u is equal to 0 in omega. So our third condition corresponds to m is greater than or equal to 2. So if we assume this mu is greater than or equal to 2, then 0 is the only solution to this equation. And also, it is known that there's a counterexample if you do not assume this condition. So that is, if mu is less than 2, then it is known that there exists a bounded classical solution to this equation. Actually, this is not our result, but this is already covered by some previous result. I mean, the paper by Biech and Punzel. Right. So, yeah. And I want to remark that actually, this is not the only solution, and actually there exists infinitely many solutions to this equation if you assume mu is less than 2. And the third assumption, third example is a Laplace type equation with a drift term, and I mean the equation has the first order term also. So yeah, okay. So the result is similar, but so if u is a bounded viscosity solution of the equation here, we add this term. So u minus dx part mu, operation of u, and minus dx part tau bx gradient of u is equal to 0 in a ball. Actually, our result cover in general domain, but here we just assume ball to show some existence, to show that there exists a counterexample in this ball. Yeah, so this B is vector valued C1 function defined on this unit ball. And if you assume for second order term, we assume mu is greater than or equal to 2. And for the coefficients of the first order term, here B is just bounded. So here we assume tau is greater than or equal to 1. Then also in this case, 0 is the only solution to the equation. And yeah, if you assume mu is greater than or equal to 2, but if tau is less than 1, then actually there exists a bounded classical solution to this equation. Yeah, and this is also the result. The existing part is by Biagin-Punzo. But so in our result, we assume that viscosity solution. So let us consider this fully nonlinear equation. Yeah. So this is first examples. So assume U is the solution of this equation. I mean, second order Hamilton-Jacobi Isaac equations. And here we take infimum and supremum over some index sets, theta and capital lambda. And the coefficients of Hessian phi lambda theta is a function defined as omega, and it's a matrix valued function. And also the coefficients of the gradient u, I mean b lambda theta, is also vector valued functions. And we assume that these phi and b are continuous for each lambda and theta. And also we assume that this function can be decomposed in this form for some sigma lambda theta. And here sigma is n times m matrix. So if we consider this equation, and also we, to check our assumption on F, especially the third assumption, we need the sigma and b is bounded from above by constant times d of x distance function. Since this phi is sigma times transpose sigma, this is actually quadratic. So, and for the quotient of first order, we only assume the degeneracy of first order. So if we assume this, then the solution for this fully linear equation, there is the only solution. So we can say that. And also, so there's another theorem for parabolic version. And here we consider in more general way. So let omega be a domain of C1 class and operator H. In this time, this H can be can depend on solution itself. So we assume H is continuous in omega and times R and Rn and Sn. So actually this is the first assumption on F in elliptic case, right? And we assume this operator H is an elliptic operator. So this is a second assumption on F when we consider elliptic case. So the assumption is like this. So in this case, we consider more general boundary condition. I mean, this operator H converge to some function G. But this function is defined only on the boundary and times R. So, and this difference between H and G, and if we take supremum over X and Y, but Y is the boundary point, and the distance between X and Y is less than delta. So when X goes to boundary, we consider the case X goes to boundary. And again, we assume these conditions on P and X. And we take a supremum over R. And we assume that if delta tends to 0, and this time this difference also goes to 0. So this is like the third assumption on F when we consider the elliptic case. Right? But in this case, we consider a more general way. So, and also in this case, we include the solution U in operator H. So we assume also some non-decreasing condition on H on R. And the first condition is this. So if we consider unbounded domain, this assumption is needed. So if P and X goes to 0, then H of X 0 PX is 0. So this is 4 assumptions on operator H when we consider parabolic inversion. So here, so our result is like this. So let us consider the U as a bounded viscosity solution. And here omega times 0 to capital T, and bounded viscosity solution to the parabolic equation ut plus h of x u and gradient of u and Hessian of u is equal to 0 in omega times 0t. And yeah, also here we consider the equation in viscosity sense. And if we assume this solution is continuous up to boundary, I mean, in omega bar times 0 capital T. And also we assume in the initial data, U is equal to 0, identical to 0 at the boundary. So then 0 is the only solution of the equation. So this is our second theorem in today's topic. And also, as in the case of elliptic equation, even in this second theorem, we can omit this assumption if we assume additional assumption on operator H, but we skip it here. So in our second theorem, so this theorem covers the following example. I mean, the parabolic Hamilton-Jacobi-Isaac equation. So this is like the elliptic equation, just we add the time derivative of ut. But for the assumption on the coefficients of Hessian and also the coefficient of gradient u is exactly the same as in the first example. And yeah, if you assume ux at time 0 is equal to 0, then yeah, 0 is the only solution. So I just want to remark that our result covers also this type of fully nonlinear parabolic equation. So in the rest of time, let me briefly explain our proof. So this is the key lemma of our proof. So as I mentioned before, our key observation was we cannot extend the solution of the boundary in C2 sense, right? So we want to use this observation in viscosity sense, and this is actually the lemma. So if you assume omega is the C1 class, and if you assume the assumption on F1 to F3, and also if you assume the U is continuous up to the boundary, and this is a bounded subsolution of the problem P, with U of x0 is positive at the boundary for some boundary point, then there does not exist test functions. I mean, for any function phi, C2 omega bar, such that this U minus phi attains a local maximum in the boundary point x0. I mean, some small Bohr centered at x0 and omega bar. So there does not exist this kind of test function. So this is our key observation. So let me briefly explain this lemma. So assuming contradiction that there exists this function, and so such that U minus phi attains a local maximum at x0, and let nu is a continuous extension of the inward unit normal to boundary to omega bar. I mean, if you assume C1 class domain, there is always this inward unit normal, and we extend this. This is only defined on the boundary, but we extend this vector value function also inside the domain. Yeah. And so, and set phi epsilon xy like this, U of x minus phi of y, and we add some penalty functions here. So so suppose that this function's maximum is attained at x epsilon and y epsilon. So, because actually this function is continuous, because we assume that U is continuous up to the boundary. So this function is actually continuous in this region, and this is of course bounded. So there is a maximizer for this equation. Then actually we can prove for this x epsilon, this is inside the domain, not on the boundary. In fact, if you compare this value at x epsilon, y epsilon, and also some specific value, this x0 plus epsilon nu x0 and x0. If you put this x and y here, this term vanishes. So it remains only this term, right? And this value is actually this one, right? And so if we put this term in right-hand side and this right-hand side, put this left-hand side, then we can have this inequality. And we assume the boundedness of the solution U. So this means the right-hand side is actually bounded. U and phi are all bounded. The right-hand side is bounded. So this means this term is bounded, and also this term is bounded. So this means y epsilon has to tend to x0. I mean, converge to x0, and also x epsilon minus y epsilon has to converge to 0. So we can have y epsilon converge to x0, and also x epsilon converge to x0. And at this point, let's see the inequality again, since U is continuous in omega bar. If we take if x epsilon tends to x0, this term and this term is tends to 0. I mean ux0 minus ux0, so it should be 0. And this minus and plus has to go to 0. So this means this term has to converge to 0. And by the assumption of the C1, by the C1 assumption on the domain, actually we can see that this x epsilon has to be inside the domain. So yeah, actually. So this is y epsilon is near the boundary point. So if you consider y epsilon and take some normal vector, so y epsilon plus epsilon near x0 here, and the distance between x epsilon and this term is smaller than epsilon if we consider a small epsilon. So like this. So this means x epsilon has to be inside the domain. And this means, so x epsilon has to be inside of the domain. So we can use the definition of the viscosity solution for at this x epsilon. And also this time, our test function is this, but here we fix y is equal to y at the point y equal to y epsilon. So if we take this as a test function, then we have this inequality by the definition of the subsolution. And also we can check the gradient of also the Hessian test functions, and by our condition on F3, this term has to go to 0. And letting epsilon to 0, we can see that u of x0 must be negative, and which is a contradiction since we assumed at that point x0 u is positive. So this is contradiction. And by using this key lemma, we can show some homogeneous Drucker condition. I'm sorry, I think I'm running out of time, so I will explain briefly. So in this case, we do not assume the boundedness of the domain. So we add some penalty function to consider some maximum of u minus phi. So if you put a phi of epsilon like this, and this function has to go to infinity as x goes to infinity. So we can have some point u minus phi is a maximizer of over the domain omega. And yeah, so if there is a boundary point such that the u of x0 is positive, then yeah, we can use the definition of the viscosity solution. We can get this inequality, and which gives you contradiction also in this case. So if you use this homogeneous degree condition, so actually this proposition 1 implies that if you assume some degeneracy property on the operator f, then actually the equation generates Dirichlet boundary condition, right? So if you assume the 4 assumptions on f, then you must zero at the boundary. So by this proposition 1, and also if you use a standard argument for the maximum principle, then actually we can show that u must be identically 0 in omega. So okay, so that's all. Thank you for your kind attention.
Thank you, Erbo. So let's welcome questions from our audience. Oh yeah, Dr. Miss, could you ask Miss? Yes, please.
Thank you for your interesting talk. By the way, I heard. Can you hear me?
Yes, we can hear you.
Yes.
By the way, I've heard another type of Liouville theorem. I forgot assumptions on PD, but it states that non-negative valued viscosity super solution is only trivial one. Do you know some relation with your result?
Okay, so so the answer is no, but so before studying this kind of equation, I was studying some semilinear parabolic equation, like this Fujita type equation, right? And yeah, in this kind of equation, we assume that the non-negativeness of solution, if you assume only positive solution, then there does not exist a bounded solution for this equation. And actually, this is a very strong tool in analysis of blow-up problem. Yeah, I heard that, but I don't know in other equations there is such kind of result. Yeah.
Oh, thank you.
Yeah. And if you know that, could you send me some result? I'm curious what kind of equation it is. Yeah.
I know, but I forgot the name of paper. I will. I will seek it.
Yeah, thank you.
I have some questions, but maybe it's better that I ask by when we have informal discussions, because
Yeah, me too.
Sato-san. Yeah, please.
Thank you. So I have one question. From the definition, from the assumption of f, which is fx of 0, 0 goes to 0, and I came up with a singular elliptic or parabolic equation, like the curvature type equation, so the does similar result holds for the singular equation?
Yeah, I think so, but yeah, actually we have two theorems, and in the second one we don't assume this continuity up to the boundary, and actually this theorem is, in my opinion, is very general. So I think that we can apply for singular equation also, but I'm not sure. But yeah, in my opinion, we can apply also for singular equation. But in our second result, I mean, to show that the solution is uniformly continuous, I don't know it holds in that case for singular equation. Yeah. Thank you.
Thank you.
Any further questions? So Professor Adrian Calderon, please.
Not professor.
Oh, okay.
You
will.
Just, my question is, can these, I guess, results be, you think they could be, like, is there any hope for having these similar results for systems of fully nonlinear elliptic and parabolic equations?
I'm not sure. Yeah, it's interesting question, but yeah, I'm not sure if it holds in system. But yeah. So if you generate this equation, if we want to generate this equation, there's also hope in. So I think this is not the it's not the answer to your question, but yeah, if you consider like fractional equations, I mean, so this kind of fractional equations, then here so we can generalize this result, but I don't think I'm not sure if we can prove in system. Thank you.
Thanks.
Yeah, just a quick comment here. I think that maybe your method gonna work for weakly coupled system.
Weakly.
Yeah, maybe. I mean, strongly
agree,
coupled, there's no theory, right? Viscosity solution theory, but weakly coupled, maybe.
Weakly coupled, yes, I believe so.
Yeah, I think so.
Mm-hmm.
So that's along the line with Adrian's question.
Mm-hmm. Mm-hmm. Okay. Do we have any further official questions? Then maybe we can move on to the informal part.